Hi everyone. As always, today you'll start off with a warm-up that you can print or download from Canvas, and then try number one and the whole thing, the warm-up or anyway, just try it out, and then on pause to check the answer. All right, here are the answers. Remember, when it says, do the data provide convincing evidence? And yes, that is correct grammar. Data is plural, or data are plural, but the word data is a plural word. That means that you're doing a test. So that's the key, and tests have HOs and HAs, so those are all the things that need to be connected in your mind about how to know when to do what. So we have our P, parameter, procedure, hypotheses, and then we're doing the A, the conditions, random, 10%, large counts. Remember to use the P from the null hypothesis in the large counts because we assume that the null is true the whole way through. So we're assuming P is 0.5 and we're going to use 0.5 as our parameter for everything. And then we make the test statistic. We use the P hat from the sample for our statistic minus the parameter P from the null over the standard deviation using the P from the null. That gets you your z-score. You want to have a picture and then get your p-value. Now this one is one of those with the not equal to, so let's highlight a couple things about that. If you have not equal to here, you should have both tails. Remember, that's called two-tailed because of the not equal to, and so you have to double the p-value. So again, in the calculator, a quick reminder, we are doing second bars 2. Because I got a negative z-score, I'll keep my lower as negative infinity. I'll put in the negative z-score, negative 2.683. Now we typically round these to 3 decimals since we can use the calculator to get the answer. If you still prefer table A, you can continue rounding to 2 and using table A. And I got 0.0036. And remember, that's just the area shaded to the left of that z-score, but a not equal to HA should really be shaded on both sides since we're not indicating a direction. Being lower or higher, it could be either one, and so hit times 2, and that's where I got 0.0073. So double p-value for not equal to HA. Then our p-value is less than the alpha. We reject the null. There is evidence. So remember, the way it works is our null and alternative basically give us 2 possibilities. Either P, remember when we started these, we said either the true value really is 0.5 or something else is going on, like with me shooting the free throws, or I was lying. Either I really am, I just had a bad day, or I'm exaggerating. So every null and alternative gives us 2 possible options, and then our goal is to reject the null and conclude the alternative evidence of the alternative. Or if we can't do that, then we have no evidence of the alternative. So that is kind of how it works. And then the interval itself on the second part of this gives us a little more info because it shows us that all of the values are below 0.5. So not only is that evidence that P does not equal 0.5 because it's not a plausible value in the interval, it also tells us that P is probably less than 0.5 since all of the values in the interval are less than 0.5. So, all right, we're going to move on to our notes. Today, the lesson that I want you to pull out is, are some groups underrepresented? So we're going to be comparing different groups. Now, I'm going to have to help you guys out a little bit in the beginning, and I know this is like a tight fit, so just write really small. I had to use a different setting pen to get it to fit all on there. So just write small, and then we'll take our notes to fix some of this stuff after you do it. But to get started, I do want to fill in this first box together. We basically want you to do the 4-step process for a 2-sample test to kind of see how it works. And then there are some formulas and things that I want to fix afterwards. But before you get started, I think I should help you out a little bit. So according to FIS.org, Black and Hispanic females are underrepresented in STEM programs compared to the non-STEM programs. So a university wants to know if that's true for their student population. So they take a random sample of 300 STEM students, found that 12 are Black or Hispanics, females, and then a separate random sample of 500 non-STEM students and found that 75. So because they have a random sample and then a separate random sample, that is going to make our procedure name a 2 sample. See if I can write better for you guys. A 2 sample. And then we're comparing representation. And so if you look at what we have 12 out of 300. So I'm going to write P hat STEM equals 12 out of 300, which is 0.04. And so that's a proportion, so I'm going to write Z. Proportions are always Z. Let's do this non-STEM. N for non-STEM was 75 out of 500, a separate sample. That is 0.15. And then it does say, remember, do the data provide convincing evidence? Remember, that means test. 4. And now I have to figure out what's our parameter. So think about that. We have 2 samples, 2 different proportions, and we're comparing. So this goes back to Unit 5 and Unit 4, where when we're comparing different groups, the best thing to do is find the difference between them. So I can see here that there are 11% more Black and Hispanic students in the non-STEM programs than in the STEM programs, just by comparing 4% to 15%. And I actually subtracted. So I'm going to do P of STEM minus P of non-STEM equals the true difference. We've done this before with intervals and in Unit 5, to true difference in proportions of Black and Hispanic females in STEM and non-STEM programs at this university. Remember, phys.org already told us they were underrepresented, and it's this university that wants to test for their own students, so we have to add at this university. So now that we've decided our parameter is PS minus PN, that's where I'll put it here. Remember, the way that we write this is we do 1 or 2. I'm going to put this in red. 1 or 2, Z or T, interval or test, and then 4 parameter. And so that's how I knew to put that there. All right, now let's talk about these hypotheses. With the hypotheses, remember, we have 2 still. This isn't new just because there's 2 samples. Everything will stay roughly the same, HO and HA. And then remember, we put our parameter always. So PS minus PN. They should always be exactly the same. And I'm wondering, are Black and Hispanic females underrepresented? That means, is the proportion of Black and Hispanic females in the STEM programs less than the proportion of Black and Hispanic females in the non-STEM programs? And so that means that, will the difference be negative? We've talked about this a lot in our last units. One way that we can rewrite this is proportion of Black and Hispanic females in STEM less than the proportion of Black and Hispanic females in non-STEM, but we can operate easier with differences, and so that's why we can just move that N over and get the difference. So hopefully that helps. And then for our null, remember, we always have an equal sign. We always have the same number as our alternative. And null is always no difference anyway. And so no difference means P sub S equals P sub N. Also, they're the same. So that's just a little background about how to set up. And you will need all of this because when you get to the next few parts, we have our statistic and parameter and stuff that you're going to be filling in. I do have one thing to add. The statistic, then if the parameter is PS minus PN, then the statistic is going to be P hat S minus P hat N. So I do actually need to fill that out and get a statistic of negative 0.11. And remember that negative means that there are 11% fewer Black and Hispanic females in the STEM programs than in the non-STEM programs. So the negative is important to keep. And you have the same assumptions and conditions as always, but we have two samples, so make sure you check it for both. The general formula, I do want to make sure you remember where to find it. So here's our formula sheet. We talked about this before. The general formula is here. We've talked about it with intervals. We haven't talked about it much with tests yet, but here is the standardized test statistic. And so we have our statistic, P hat S minus P hat N. Parameter was PS minus PN, and then here we have the same formula we've been using for two proportions everywhere else. So try to do your best, and then you can unpause the video to get the rest of the answers, and we will debrief for some corrections, because you're going to need to correct a little bit of your work, no matter what. All right. So I have kind of written down what we'd already done. I maybe had added a few extra notes when we did it together, but that first box should be done. So what I'm going to do is make sure you guys see the second one. So we have STEM and non-STEM, random 10% large counts, same formula and rules. But I do want to show you we're going to make some adjustments to the large counts. So just make sure you pay attention when we come back to that. I need to do the statistical work first before we do it. So, here's our stuff. This is what you should have gotten. I do want to remind you of this Z-score. I got negative 5.621. That's second var's 2, and then I put negative. Since it's negative, I leave that negative 5.621, and then paste. And so I got 9.5 times. Don't forget about the E negative 9 times 10 to the negative 9. You'll never get a p-value that's a whole number. So if you get a number larger than 1, or a number larger than 1, I mean. So if you get a number larger than 1, then just roll your eyes to the right, look for the E and the negative, and then really that's 9.5 times 10 to the negative 9ths. Now, we have a few corrections to make. So what I want to bring your attention to is that the null hypothesis says PS equals PN, or there's no difference between them. Remember that a significance test assumes the null is true for everything, but we didn't know what PS or PN were, and so we had to use them separately in our large counts, in the formula for standard deviation, etc. And so what we can do is I'm going to teach you something new. It's going to be called P hat C. And that is the pooled or combined proportion from the two samples. So the formula for it is to take x1 plus x2 over n1 plus n2. And so in this problem, let's see, I'll just pick a different color pen, maybe purple, to show that. And so we're going to do P hat C equals, and we're going to do 12 plus 75 over 300 plus 500. And so let's see what that is. That equals 0.10875. Now what this number is let's make it the smaller font, my bad. Is it tells us the combined proportion, because remember that in a hypothesis test, we assume the null is true the whole time and that the two proportions are the same. So because we have two different proportions, 4% and 15%, and two different sample sizes, then the way that we assume that they're the same is we just combine them into this pooled proportion. So it should be the average of the two, the weighted average of the two. So in this case, it's almost 11%, which is closer to 15 than 4 because there were more non-STEM than STEM. I always check it in my head to make sure I got it right before I use it for the whole problem. And then we are going to use it for the whole problem. So what I'm going to do is I'm just going to correct where we would use it and show you how that changes a few things, and then we'll make sure we use it in the future for any future tests. So our pooled proportion is what we do when we assume the null is true. We get this combined proportion, and then we have to use that everywhere we were assuming the null was true before. So in a one sample test, we use the P from the null for our large counts condition. Remember, I started this earlier. And so here we really should be using P hat C and 1 minus P hat C there and here. So I just kind of wrote over those with P hat C, which means I really should be checking that 300 times 0.10875 is at least 10, and it's 32.6, so 33, we round up. And then 300 times 1 minus, so 0.8189125, and that's 267. So those are still true. And again, I can write it in the purple if you want to see it, that we do 300 times we'll just do 0.11 is at least 10, and then 300 times 0.89. And we'll do it again over here. We should be using the same number both times to assume the null is true. And then get our large counts that way in the future. The next place it matters is this formula right here for the standard error. Remember, we assume the null is true, and in a one sample z-test for a proportion, we use the p from the null. And so here we have two separate p's, but we don't know what either one is. Our null says that there's no difference between them, and so we have to use the p hat c here as well. So I'm going to put p hat c, 1 minus p hat c, 1 minus p hat c. Everything else stays the same. And so instead of using 0.04 and 0.96 and 0.15 and 0.85 separately, I should have been using the 0.11 and the 0.89. So again, I'll show you what that looks like. That would be z equals negative 0.11 minus 0 over, and it would be 0.11 times 0.89 over 300 plus 0.11 times 0.89 over 500. And when we do that, we get a different z-score. So we will just calculate it really quickly. You guys can do the same. And we get negative 4.814 this time. Now, that doesn't make much of a difference in terms of our conclusion. If I do second vars 2 with my calculator and do that, I'll show you right here. Second vars 2, and it's we're looking at negative z, so we start with negative infinity, and we put in negative 4.814, 0 and 1, then I get 7.4 times 10 to the negative 7. So it doesn't change the outcome because that's still 1, 2, 3, 4, 5, 6 zeros before I put that number 7. And I'm not worrying about changing the S. But officially, I'm going to write in red on the left the formula for the test statistic because that's what's different. And in the A section, I'm going to write in red the normal condition. or the large counts condition. So this will be our official notes for you to add here. Z equals P hat 1 minus P hat 2, always 0 for the second part because it's really PS minus PN, and that's always 0 from the null where it says no difference, where P1 equals P2, it'll always be 0. And then on the bottom, we have square root P hat C, 1 minus P hat C over N1 plus P hat C, 1 minus P hat C over N2. What that does for our large counts means we do N1 times P hat C is at least 10, N1 times 1 minus P hat C, oops, my at least are ugly, is at least 10, N2 times P hat C is at least 10, and N2 times 1 minus P hat C is at least 10. And what that tells us there is if the null were true, these proportions would be the same. For the proportions to be the same, these are the number of successes and failures we should have had for each group. And so that's how that works. So a little bit different. And I'll show you on your formula sheet where it all comes together. So look at this standardized test statistic. We have in the blue, sorry, it's a little slow. There we go. In the blue, highlight here, statistic is your difference in sample proportions. Parameter is the difference in population proportions, which will always be 0 for us right now. And then the standard error. So when we look at the next page, we have our statistic, our parameter, which is always 0 for a test. And then we have our standard error, and this is right here when P1, P2 is assumed. They have this formula right here, and they give you what that P hat C equals, and they just make it a little simpler by factoring out the P hat C since the numerators are the same for both fractions. I still like to write it so that it's the same format, but you can do whichever one you'd like. And so that's on there. I'm going to let you guys copy all of this down, and then you can try to check your understanding. One thing about this, before you move on to the check your understanding, is that I wrote the formula on the other page with this P hat C distributed, and either one is fine. Honestly, in the calculator, it's faster to write them separate, but either one is fine. And then one other thing, this could be P1 equals P2, and that's fine too. So if we look at our steps, we have P, A, S, S, all 4. Now give it a try in your check your understanding, and then we'll go over that answer to make sure you get it. Okay. So in this one, I ran out of room to do the second one, but just to show you the first one. So we have our P. I want the bigger one now. Okay, we have our P. So we have our procedure, our hypotheses. That's always 0. And then our parameter here defined. You can put these things wherever you want to. So I just like to write them down somewhere so I can use them in the formula later. And then one other thing about that is for this inequality, it's up to you which order you want to decide to subtract. One thing that I find may be easier, so it says, do these data provide evidence that preschool reduces the later need for social services? So that would mean preschool is less than not preschool. The proportion who need social services is less for preschool than for not. And then we'd like it to be a subtraction, so then you can subtract the in over. And if I move it over, then that's how I get the less than 0. So sometimes it's easier to start there and then write your HA first. And so you can get the order of the subtraction that you want to use and then make it the same for your HO. And remember here we're using our P hat C here and here. And that was 1 minus P hat C. We always round up. And you always want to say approximately normal afterwards. This formula, again, I could have factored out the P hat C, 1 minus P hat C, like the formula sheet shows. So that's fine. You're going to need to get used to seeing it both ways. And so we have our z-score, our test statistic. Just a couple of reminders. I like to have the normal curve picture. We have our p-value, all necessary. Oh, don't forget this alpha up here. And then our conclusion is the same as always. So we compare the p-value, reject or fail to reject, there is or isn't evidence in context. Now, number 2, I forgot, I ran out of room when I was making this answer key. And so I just did really basic. What I wanted to remind you about with number 2 is that we're using all the same p hats, but this formula, it does not use p hat C. And the reason why, basically it's just all about the logic behind a significance test compared to a confidence interval. In a confidence interval, we're not pretending to know what each of the p's are. We're trying to use an interval to estimate the difference. So it's not something that we are assuming. We're not assuming anything. And so we just use what we have. In a test, the whole logic of a test is to assume the null is true, and the null says they're the same. So we use that p hat C throughout to make that assumption fit. And so that's a key difference between them there. So I didn't interpret it, I didn't have room, but we would just say we are 95% confident the interval from negative 0.347 to negative 0.033 captures the true difference in preschool and non-preschool people who later need social services. Okay, so you have some homework to try. Give it a shot. Let your teacher know if you have any questions, and see you next time. Thank you so much.